All right, so let's look at the problems I assigned from section 1.5. So this section's all about solving first order linear differential equations. Typically, these are not going to be separable, so we need another approach for these. And generally, the approach we take on these is to find integrating factors. So the way we find integrating factors is by finding, whatever. Let me back up a bit. So what form does a first order linear differential equation take? So we have y prime minus some function in our independent variable times our dependent variable. So the thing that makes these equations linear is that the dependent variable only exists in its simplest form, only exists as y. So does not exist as y squared, e to the y, anything like that. It just exists as y. So the other functions that show up in terms of the independent variable, they can take whatever form, but the functions that are in terms of y, we have to have first derivative. That's the first order part of this, and they have to be linear. So that's what stipulates that we can only have y here. So when we have equations of this form, by the way, this should be generally plus. When we have equations of this form, we want to multiply through the equation by this thing called integration factor. And what do those look like? That's going to look like this. I'm going to take e and raise it to the integral of whatever this p is. So the integral of px dx. So for us, let's find the integral of negative 3x to the negative 2 dx. That's going to give me negative 3x to negative 1 over negative 1, which gives us 3 over x, which means that our integrating factor is going to be mu of x equals e to the 3 over x. All right, we call this an integrating factor because it's a factor I want to multiply my entire equation by. So let's do that. So I get e to the 3 over x, y prime, minus 3 over x squared, y, times e to the 3 over x equals e to the 3 over x. Let's just put it all together. E to the 3 over x over x squared. All right, so what is the point of using the integrating factor? 1 second. Okay. So the reason we use the integrating factor is to make integration possible. And the way it makes integration possible is the left-hand side of this equation now. This now resembles the product, the derivative of a product. And that product is y times our integrating factor. So e to the 3 over x. And just for this first example, we'll go ahead and verify. Let's actually go ahead and do this integral. When you do the derivative of a product, first thing you do is take the derivative of y, so that's y prime, and that should be multiplied by e to the 3 over x, just left intact. So that's this left-hand term here. And then the other part should be y times the derivative of e to the 3 over x. So the derivative of any exponential function is going to just contain that exponential function e to the 3 over x. But because of the chain rule, we want to take the derivative of 3 over x. What is the derivative of 3 over x? I would like to divide that or rewrite that. So that's equal to the derivative of 3x to the negative 1 which will be equal to -3 times x to the -2, which I believe is what we have. So just to make sure that we actually have the derivative of a product the way we want it, and then the right-hand side is going to look like what? E to the 3 over x squared. All right. So now that integrating factor did indeed allow us to integrate. So I'm going to go ahead and integrate both sides with respect to x. On the left, the integral and the derivative are inverse operations, so that allows me to just write y e to the 3 over x. The right-hand integral, this might be a little more complicated, so let's talk about how to deal with it. So I think we should probably set up a u substitution. So let's give ourselves a little more room to make this happen. I want to do the integral of e to the 3 over x squared dx. I'm going to let u equal 3 over x, which means the du will be equal to, we already did this, -3 over x squared dx. Okay, so how do I transform the rest of this integral? So let's do it in pieces. I see in the numerator, I have e to the u. And the rest of this, I would love it if I could make dx over x squared show up. So I'm going to go ahead and try to make that happen with my my du here. So I'm going to go ahead and divide both sides by -3. So -1/3 du is equal to dx over x squared. So actually, let's do that before I make any substitutions. E to the 3 over x. Actually, let's go ahead and try to think of the right way to illustrate that this will actually work. For now, let's just say e to the u over x squared dx. All right, and the dx over x squared, what is that going to be replaced by? That is going to be replaced by the -1/3, which I'll pull out outside the integral. And then the rest of this just becomes e to the u du. What is the integral of e to the u du? That is simply e to the u. And if we undo our substitution, we get -1/3 times 3 over x, which is -1 over x. Okay, so the right-hand side here is going to be -1 over x plus c. We don't have enough information to figure out what c is. So our last move is going to be to isolate y. So y equals -1 over x plus c over e to the 3 over x. We have a fraction within a fraction, which might bother you. So if it does, we can multiply numerator and denominator by x, and that will give us this. Y of x equals cx minus 1 over xe to the 3 over x. So either one of these is perfectly acceptable, or anything else you have which might be equivalent. All right, moving on. All right, now we have an initial value problem. All right, so do we have the form that we want? So just a reminder, in general, we want this. We want our derivative term plus, some function in p or in t times our dependent variable, not differentiated, equal to our some function in t, another function in t. I think we're already in that form. We're not dealing with y's, we're dealing with x's. So again, our first move is going to be to figure out what our integrating factor is. So in this case, our p of t is -5, which means that our mu of t is going to be e to the integral of -5 dt, which is equal to e to the -5t. All right, so that's my integrating factor. So I'm going to multiply my equation through by that. So e to the -5t dx dt minus 5x e to the -5t equals e to the -5t sine 2t. Okay. Now, just like last time, the reason we do that integrating factor, multiply by the integrating factor, is to wind up with this, derivative product, dependent variable x times our integrating factor e to the -5t equals e to the -5t sine of 2t. Now we can integrate both sides with respect to t. So on the left, we get x e to the -5t. On the right, we get this is going to be a little more complicated. So on the right, how are we going to have to deal with this? So we have two functions multiplied by each other. So that typically lends itself to integration by parts. So let's make ourselves some room to set that up. So my two parts are going to be the exponential e to the -5t and the trig sine of 2t. I don't think it matters which one you assign to which part. Neither one is really going to get any simpler. All right, so if those are u and dv, then what's du? Du will be equal to -5 e to the -5t dt. V will be equal to -1/2 cosine 2t. And let's just let me double check that. Yeah, okay. So what is the integral? How does integration by parts work? Integration by parts work. The integral of u dv is equal to uv minus the integral of v du. So for us, this is going to be uv is -1/2 cosine 2t e to the -5t minus the integral of v du. So that's going to be plus 5, the integral of 5/2 e to the -5t cosine 2t. Unfortunately, it looks like we got to do integration by parts again, so we'll go ahead and set that up again. Before we do that, I'm going to go ahead and write the 5/2 on the outside of the integral, and I'm going to assign the parts of the integration by parts in a consistent way. So u is going to be the exponential part, dv is going to be the trigonometric part. So dv equals cosine 2t, du will be the same as it was, -5 e to the -5t. V will be equal to 1/2 sine of 2t. Okay, and we can basically apply the formula again. So uv will be 1/2 sine of 2t e to the negative 5t minus the integral of v du, which is going to be minus 5/2 times the integral of e to the negative 5/2, no, e to the negative 5t sine 2t. So it looks like this integration of parts is just going to kind of bounce back and forth forever. Unfortunately, it's not going to, and let me show you why. So remember where we started. We started by, this whole process was to set up this integral. The integral of e to the negative 5t sine 2t. And so far, what have we come up with? This has been equal to negative 1/2 cosine 2t e to the negative 5t plus, just make a new line, plus 5/2 times this integral, but even this integral we did something else with, plus 5/2 times this, 1/2 sine of 2t e to the negative 5t minus 5/2 times the integral of e to the negative 5t sine 2t. So let me do one more step to simplify some stuff here. Let's just, expand. So negative 1/2, move over a little bit more. Negative 1/2 cosine 2t e to the negative 5t plus 5/4 sine 2t e to the negative 5t minus 25/4 times the integral of e to the negative 5t sine 2t. So here's what I have now. On both sides of the equal sign here, I have a term that involves the integral of e to the negative sine 2t, sorry, e to the negative 5t times the sine of 2t dt, which I'm going to go ahead and, just to save space, I'm going to call I. So basically what I have is this. I equals negative 1/2 cosine 2t e to the negative 5t plus 5/4 sine 2t e to the negative 5t minus 25 over 4i. I'm going to go ahead and bring that 25 over 4i to the other side. So 4/4 I plus 25/4 I, so it'll become 29 over 4i equals negative 1/2 cosine 2t e to the negative 5t plus 5/4 sine 2t e to the negative 5t. And our last move here is to divide by 29 over 4. So I equals, what is negative 1/2 times 4 over 29? That should be negative 2 over 29, I believe. Yeah, negative 2 over 29 cosine 2t e to the negative 5t and plus 5 over 29 sine 2t e to the negative 5t. All right, so kind of a long detour. So why did I do all that? That was all to get the right-hand side of this equation, essentially. So for now, I'll just write it like this. X times e to the negative 5t equals I plus c. So let's go ahead and figure out what c is, because we do have the means to do that this time. So we'll go ahead and plug in 0 for t, pi for pi for x. All right, so x, so pi times e to the 0 is 1 equals, okay, what happens when I plug in 0 for all these t's? The right-hand term will vanish because sine of 0 is 0. The left-hand term, oh wait, sorry. Yes, no, sorry, sine of 2 pi is 0. Cosine of 2 pi is 1. So I get negative 2/29. So just one more, let me just double check that that's really all that comes out of I. When I plug in 0 for t, cosine of 2 times 0 is 1. E to the 0 is 1. Sine of 0 is 0, so that whole thing goes away. Okay. Plus c, which means I get this. C is equal to pi plus 2/29. All right. So we're almost there. I'm going to write my answer at the top of the page because that's the only place where I feel like I can delete something and keep going. So what is our final result here? If I can write it all in one shot. X of t equals this. Well, it equals I plus c. So negative 2/29 cosine 2t e to the negative 5t plus 5/29 sine 2t e to the negative 5t plus c, so plus pi plus 2/29 all over e to the negative 5t. Probably could make that a little more simplified, but I'm going to go ahead and leave it at that. All right, moving on to the third question. All right, a 600-liter tank initially contains 200 liters of water containing 10 kilograms of salt. Suppose the water containing 0.1 kilograms of salt per liter flows into the top of the tank at 10 liters per minute. All right, so we have a mixing problem here. So typically with these, the first thing we should figure out is what variable should we control for? And I hate saying always, but pretty much always, from what I've seen, the independent variable we should control for is time. You know, just look at the final question that we're asked to answer. When the tank is full, I want to know something. So we should probably control for time. And accordingly, how much salt is in the tank. So I think because of that, I should control for a rate of, the rate of change of salt over time. So let's talk about how that is going to be measured. How am I measuring how much salt there is in this tank? Like what unit? Looks like I'm measuring salt by mass in kilograms. And how am I measuring time? I'm measuring time in minutes. So I think it's really important to make sure we're consistent. So whatever rates we figure out need to be consistent with this kilograms per minute. I am going to break this down into two rates, ds in, dt, and ds out, dt. Okay, so what's coming in? All right, 600-liter tank initially contains 200 liters of water containing 10 kilograms of salt. Suppose that water containing 0.1 kilograms of salt per liter flows into the top of the tank. Okay, so this is not exactly the rate I want, but it's a good means to an end. So I know the water that's coming in is 0.1 kilograms of salt per 1 liter. 1 liter of water. So that's kilograms per liter, which is not what we want. So I hopefully have a way to multiply this by the number of liters per water come into this tank every minute, which is what the rest of this says. And that water is flowing into this tank at 10 liters per minute. So that's my rate in, at least part of it. Let's keep looking. The water in the tank is kept well mixed. Okay, so I think this is complete. This is the only water that's coming in. It's a constant flow rate. And also the concentration of the salt that's coming in is also uniform. So I think my rate here, the inflow rate, I'm getting one is, and let's make sure it's kilograms per minute. So liters of water, those cancel. I get 1 kilogram of salt per minute. Okay, so I feel good about my incoming salt rate. What's leaving? Okay. The water in the tank is kept well mixed and 5 liters per minute are removed from the bottom of the tank. All right. So something to keep track of here is that let's stop thinking about salt for just a second. Let's just talk about how much water is coming into this tank. So at the start, there's some water. How much water is coming in? Like, what's the rate of water coming in? 10 liters per minute. What's the rate of the water coming out? That is 5 liters per minute. Which means every minute this tank is gaining 5 liters of water, which is that's going to be an important piece for figuring out the rest of this equation. So you're told that the water is well mixed when it leaves, and we know that 5 liters per minute. So how many kilograms of salt are in this tank? Well, we don't know how many, but we're giving it the name S. So S kilograms of salt, and that's dissolved over how much water? I don't know, but I can generalize it. I know it's going to be 200 plus 5 times T. Liters of water. And how much of that is leaving every minute? 5 liters of that water is leaving every 1 minute. So since my water is well mixed, I can assume that, whatever the mass is of salt, it's evenly spread out over the full volume of water, which is initially 200 liters, but that's going to grow every minute. How much water is leaving every minute? 5 liters. So now, do I have kilograms per minute? Yeah, I should again. Multiplying through gives me this 5S. I don't like the fact that those look so similar. Over 200 plus 5T. One thing I'll take advantage of is that every coefficient in this fraction is divisible by 5. So I'll divide everything by 5 and I get S over 200 divided by 5 is 40 plus T. So here's my equation. ds over dt equals the the inflow rate, which is 1 kilogram per minute, minus S over 40 plus T. All right, so here's our differential equation that I want to solve. How do I solve it? I want to put this in the form that we've just been dealing with. So let's move some things around. ds dt equals, or sorry, ds dt, and then I want to move over my other variable term. I'm also going to kind of separate this out. 1 over 40 plus t times s equals 1. So this is a first order linear differential equation. My integrating factor is going to come from e to the integral of 1 over 40 plus t dt, which is going to be equal to e to the natural log of 40 plus t, which is equal to 40 plus t. So what happens when I multiply through by 40 plus t? I get 40 plus t ds dt minus 40 plus t times 1 over 40 plus t. I think I just get minus s equals 40 plus t. All right. And the reason we do this is so this looks like the output of the product rule. So the product of s and our integrating factor, which is 40 plus t, equals 40 plus t. Integrate both sides with respect to t. And I get s times 40 plus t equals the integral of 40 plus t, which is 40t plus 1/2 t squared plus c. And before I go further, I'm going to go ahead and figure out what c is. Do I have an initial condition here? A 600-liter tank initially contains 200 liters of water containing 10 kilograms of salt. Okay, so that tells me that S of 0 is equal to 10. Okay, so we'll go ahead and plug those things in. So S is 10, T is 0, so 10 times 40 equals 0 plus 0 plus C. So C is equal to 400. Okay, so this will be my full equation. S of T equals this. 40T plus 1/2 T squared plus 400 all over 40 plus T. So this is the solution, the analytic solution of this function I was trying to find. But now it wants me to evaluate this at a certain point. How much salt is in the tank when the tank is full? So when's the tank going to fill up? When's it going to become full? When's it going to fill up? So it initially has 200 liters of water in it. When it's full, it will have 600 liters of water in it. So I'm basically it needs to gain 400 liters of water. And I know it gains 5 liters of water every minute. So 400 liters divided by 5 liters per minute. I think in 80 minutes, that's our time when this fills up. So I want to evaluate this function at 80. So what is the amount of salt that's going to be in here at 80 minutes? Let's go ahead and find out. So 40 times 80 plus 1/2. Okay, I have an approximate answer of 56.7 kilograms of salt. All right, so that's all for question 21. All right, moving on to question 22. All right, so a manager in a communications company contributes $2,400 per year into a retirement fund by making many small deposits throughout the year. The fund grows at a rate of 3.5% per year, compounded continuously. After 35 years, she retires and begins withdrawing from the retirement fund at a rate of $3,500 per month. If she does not make any deposits after she retires, how long will her retirement fund last? Okay, so, and this hint is useful. I want to divide the problem into two smaller problems. So basically, it's going to be a piecewise function we end up coming up with. So basically, one for the time while she's working and one for the time after she leaves her job. So while she's working, the account's only going to grow. So let's talk about how it's going to grow. I'm going to call this account DMDT. And I think the way it's described is there's a couple ways this account grows. One way, okay, so before we go any further, let's be clear about the units. This is going to be dollars per year. So that's the unit we're going to be making sure we're consistent with. Okay. So while she's working, one way that this account grows is going to be through her, monthly contributions or her continuous contributions. And that happens at a constant rate. So she puts in $2,400 every year, which I'll represent with just a constant number, 2,400. That's a constant rate. The other way this account grows is that the fund grows at a rate of 3.5% per year compounded continuously. So compounded continuously, that's we can kind of use that language interchangeably with, it grows at a rate proportional to its size. And beyond that, we're told what that proportion is. That's what this 3.5% is. So 2,400 plus, we'll convert it to a decimal, 0.035 M. So this is how her account will grow while she's working. So I got two different components here. There'll be a linear component, which comes from the constant rate of change, and there'll be the exponential component, which comes from this 0.035 M term. All right, so that's how much money, or that's the rate of change, that's the differential equation for while she's working. So how's this going to look after she retires? So retirement. So after she retires, what things are going to change? So let's read the rest of that question. After 35 years, she retires and begins withdrawing from the retirement fund at a rate of $3,500 per month. Okay, so now the account is going to shrink because she is going to withdraw money at the rate of $3,500 per month. I cannot use that value as is, though, because one thing we got to keep note of is that our time base is years. So I want to multiply $3,500 times 12. So I'm going to lose $42,000 every year from my retirement account. Is that it? Will my retirement account is that the only rate that I have to worry about? That I have to concern myself with in this account? No, because you're still earning interest on whatever's in there. So because of that, I still have this term of 0.035 M. Okay, so I believe these are my two equations. Let me just make sure there's nothing else going on in here. Okay, so she's working, and this is going to be from 0 to T, or sorry, 0 to 35 years. And retirement is going to be from 35 to a time we are told to figure out. Okay, so how do we find this out? So we want to know how long her retirement fund is going to last. So I think one thing we need to figure out is how much money her retirement fund has in it when she retires. So to do that, we need to solve this equation. So to do that, let's go ahead and put it in a friendly form for solving a first order linear equation. So dm dt minus 0.035 m equals 2400. The integrating factor will be e raised to the integral of this coefficient, which is a constant. So that'll be e to the negative 0.035 t times dm dt minus 0.035 m times e to the negative 0.035 t equals 2400 e to the negative 0.035 t. Now we'll rewrite this as a derivative of a product. So the integrating factor times m equals 2400 times e to the negative 0.035 t. Integrate both sides with respect to t. So e to the negative 0.035 t times m equals 2400 over negative 0.035 e to the negative 0.035 t plus c. So let me go ahead and approximate that coefficient. 2400 divided by 0.035. So 68,571. So e to the negative 0.035 t equals negative 68,571.43 e to the negative 0.035 t plus c. I just left off the m, didn't I? M. Okay. So let's go ahead and pause here. I have enough information to figure out c, because I think I'm told, or am I told, or is it just strongly implied? I think we have to assume that when t equals 0, we're not told that her company like preloads her retirement account or anything. So I think when t equals 0, m equals 0. So what does this mean about c? So when m equals 0, the left-hand side of this equation will equal 0. Will equals negative 68,571.43 plus c. So c will equal 68571.43. So the equation here is going to be m of t is equal to 68,571.43 e to the negative 0.035 minus 68,571.43. Actually, it's not quite true. Skipped a step here because this e term is still over here. So what happens if I divide off that exponential term? So if I divide both sides by that term, then what happens? Well, then this is going to cancel out. This is going to cancel out. And then this will have e to the positive 0.035t. I'm just double checking because this makes me uneasy. Because the way this is written, it looks like this account is it looks like this account starts with money and loses money as time goes on. Because when t equals 0, all right, yeah. I found my suspicion here. So if I go back to this step here, if you can see my cursor, so I have this negative 68,000 number times this exponential term. If I multiply both sides by this e term, which I did correctly, but then I just didn't carry correctly here. So basically what I have is I have all my signs flipped down here. So whoop. To repair that, I'm going to just change this here because I think this makes the behavior more what I want. So basically, what does this say now? Now, when time is equal to 0, this whole value will essentially be equal 0. But as time passes, this term on the left will get bigger. So my account will grow, which is what I want. Okay, so what did I want from this equation? Well, what I wanted for this part of the problem is to figure out when she retires, what is she retiring with? So I'm going to plug in 35 for time, go to my calculator and figure out how much money she has when she retires. All right, and I am getting a grand total of 164. $164,857.11. All right, now we're ready to move on to the post-retirement phase of this problem. So after she retires, we want to know how long that money will last. So we have another equation to solve here. The good news is this equation is going to have very much the same structure. So I'll go ahead and rearrange. So dm dt minus 0.035 m equals negative 42,000. Can I rely on anything I just learned to kind of help me here? The left-hand side, so the integration factor is going to be exactly the same, which means the left-hand side is going to be ddt of m times e to the negative 0.035 t. I needed to multiply the right-hand side by negative 42,000. e to the negative 0.035 t. And I think from here I should probably resume. So what do I get if I integrate from here? If I integrate both sides, I should get m times e to the negative 0.035 t equals negative 42,000 over negative 0.035 times e to the negative 0.035 t plus c. So again, I don't want to carry that strange fraction around, so let me go ahead and evaluate it. 42,000 divided by 0.035 gives me 1.2 million. So m times e to the negative 0.035 t equals 1.2 million e to the negative 0.035 t plus c. All right, do I have enough information to figure out what c is? Yes, I do. I know that when let's do this to make our lives easier. Let's reset time. Let's go back to t equals 0. Just to make our lives easier with the e's here. So I'll say m equals 0 is equal to what? Now, my initial value for the account is going to be whatever I retired with. So m of 0 will be equal to 164,857 and 11 cents. Okay. So when I plug in 0 for t, e to the 0 is 1. So on the left-hand side, I'll have 164,857.11 equals 1.2 times 10 to the 6th times 0, or no, times e to the 0, which is 1, plus c, which gives me that c equals 164,857.11 minus c is equal to negative 1,035,142.89. All right. So now let's write this equation. M of t is equal to 1.2 times 10 to the 6th. Now I'm basically dividing through that exponential, trying not to mess it up this time, plus c, which is minus 1,035,142.89 times e to the 0.35 t. Was there anything else I have to worry about here? That should be it. Now, what am I doing with this? I want to know where this thing equals 0. I'm going to go ahead and, I know we've come this far, but I'm going to go ahead and take this to Desmos. So what is our equation? 1.2 million minus 1,035,142.89 times e raised to the 0.035x looks like I found a 0. So how long is it going to last? Not very long. If we did this correctly, it looks like it's going to last about 4.22 years. So that is going to be our final result here, 4.22 years. All right, and that is all for this section.